Yes, here we are. Once again, it's the physics video lecture. Actually, it's the physical science, psci 168, the video lecture 8. And I hope everybody had a chance to look at the Wally Wallington video. We're going to build on that, no pun intended. So what we're going to do today is talk about the balance, the lever. Then I'm going to do a big full-width board picture of what Wally Wallington was doing because we want to analyze it so we really understand it, where he lifted up that gigantic concrete beam just using his own strength, right? And then we're going to get into work and energy, so we'll finally arrive at the energy concept today. And okay, so let's just get started. The first thing is we're reviewing the balance. And we have some uniform object we suspend in the middle here. And then we can have a larger weight balanced against a smaller one. 1, 2, 1, 2. I'm going to label it that way this time, because we knew that we had force 1, L1 equals force 2 times L2. So that was the law of the balance. Just like a teeter-totter, you put the big, in fact, didn't Wally Wallington say that? You put the big kid towards the center, right? So that's the law of the balance. And then the lever is really the same law as the law of the balance. Okay. You have a fulcrum there. And the examples of leverage are just so great. Let me put a note here. You want to print out some good leverage examples, namely from the Wally Wallington video. Okay, because he shows great examples of leverage as well as the beam that I'm about to do. So print out images. You should be able to come up with some great images. Okay, then this very important concept of center of mass. It's the balance point, and in the symmetric object, it's literally the geometric center. So, because this is a uniform rod here, at halfway, at the midpoint, is where the center of mass is, and I can balance it there. See, the key though is that the weight of this thing, if I put it on the scale, it weighs a Newton or something. If I bring the right scale for that, yeah, it weighs a few newtons. Okay, nothing wrong with that. A couple newtons. It would weigh the same amount if I stood it up on end. Okay. So it has a certain weight, but by balancing it at a certain point, the center of mass, I can say the weight is concentrated in terms of the weight vector, the force vector, it's concentrated at the center of mass. Okay. So I think I stated that last time. That's such an important point. So the weight of an object, the weight, which is a force, it acts at the center of mass. And this balance example is so good because you can literally just demonstrate it. Okay. That means that this beam has a weight, but it acts right there at the center of mass. Okay, center of mass, balance point, we talked about that before. So what I want to do now, this is one of my main goals for the beginning of the hour, is to analyze what Wally Wallington did with that giant cement beam, 19 tons of cement, or however much it was. So I have to make a reasonably large drawing here. So first I'm just going to indicate this beam here. This is that big concrete beam that he's actually lifted off the ground with his own power. And we want to see the technique. Now the technique is, I gotta measure this off reasonably. He built this cradle in the middle. Here's what I'll do. So he built this wooden cradle that is something like this, and he was rocking this beam up and down the thing. Let's make sure we have the equal length on each side. This much. This side needs to be extended a bit. There we go. Okay, so there's the beam. There's that cradle. Once more. Good. Let's see. Yeah, good. That's symmetric enough. So you have the cement beam, you've got these wooden 2x and what have you here, and he's gotten it this far off the ground already. And he's somehow rocking it back and forth. Okay, so how is he rocking it up and down? He's built in a bunch of wood already here. Okay, so he's gotten it that far. Okay, so what he's going to do is tip it up. So here is now the fulcrum. I'll make this one red, just so, well, whatever. I'll make the wood red, the fulcrum blue. Okay. So we have that there. And we have all that wood in here. Okay, so we have to make this big enough so we can get this analysis. So the point is, where is the center of mass of this beam? It is right here in the center. Okay, it's in the center. So right now, you'd be resting on both of these things. It's resting here and here. Okay. So the law, now how does the law of the balance and the law of the lever come into effect? This blue dot, this is the important one. This is the fulcrum. And what does our law of leverage give us? There's actually more length on the left than there is on the right. So how do you make a balance? You do a balance by adding a bucket. Okay, so he adds a bucket of cement. Added, or let's make sure, because it was a bucket there, he was carrying a bucket back and forth, so bucket of cement. Okay, so here's the thing. Now I'm going to get rid of this red in our drawing. This is important because we have here, this is the entire weight of the 19-ton beam. That's my point. That's the entire weight, and it's balanced right. It's acting right at the middle. So this is the beam. The weight of the bucket is here. So this is force sub 2 equals the weight of the bucket. This here is F sub 1 is the weight of the beam. Okay, one of these you can carry by hand, one of these is absolutely giant. Okay? So where's the law of the balance here? My L1 is just this little distance. How could we indicate this best? My L sub 1 is the distance between these two arrows. Right? It's half the width of the cradle. That's my L sub 1. What's my L sub 2? My L sub 2 is the distance from here to the center of the bucket. So because the weight of the beam is concentrated right there at the star, when we write F sub 1, L sub 1 is equal to F sub 2 L sub 2. This L sub 2 is huge, this F sub 2 is small, this L sub 1 is small, and this F sub 1 is huge. So this picture is the analysis of that, and that's why he can now balance it on that blue dot there, and it's going to tip up. Then he shoves in that extra piece of wood, and he walks over to the other side and repeats it, and so he was able to rock the thing out. So this was a fantastic example of the law of the lever, and it just gives you respect for people who can build something. This was just one man's strength to lift that gigantic beam. Okay, one of the all-time great videos. So go ahead and get, if you don't already, study this video, because there's more good material there in 6 minutes than you could ever get. And get some good screenshots of everything that's being done there. But this here, this drawing is the analysis. It's just the law of the balance applied. Law of the balance applied to the Wally-Wallington thing. So let's go ahead and write this up here again. Wally-Wallington video. And that is in the playlist. I hope you had a look at it already. If not, you absolutely have to look at it and compare it to what I'm showing here. Very good examples of leverage. Other examples as well. This thing, you want to do a printout and make sure you understand this picture here. Again, this is the weight of the entire beam, but it's just this far here, the L1. Okay. Whereas this is the weight of the bucket, but it's that far there. That's these two products that are the same. Okay. So giant force, small length equals small force, large length. Okay, that's what I wanted to show you guys before we move on. So now we're going to introduce the concepts of what this class is named for. We want to get to the energy concept finally. But we've made a very thorough approach. And I think at this point, I hope you see the technique that we're using to build up our theory. Because everything is based on what came before. And historically, we're still at the place where giant monuments were being built out of stone just with manpower. More than one man for sure, but now that you see that, you see the power of leverage. Okay, so next we're going to introduce the concept of work. And let me just write here, work, energy, work, energy, power, because they could say that's our new chapter. Work, energy, power. So work, and I'll just give the definition and we'll move through it. Work is equal to a force times a displacement. And I immediately give the basic example. Is this thing here is a 10 Newton force. Pretty sure my scale is visible and reading 10 newtons, that's right. And a liter of water is also 10 newtons, or 9.8, but we'll say 10 for now. Okay, so if you need to know a 10 Newton force, you just got a liter bottle of water, because you don't always have a chunk of metal at hand that is also those 10 newtons. So what is the work? If I have a force and I'm holding up this 10 newtons against gravity, if I displace it, what's the best view here? There's a meter stick. So I just have to lift it 1 meter, okay? Force, it's 10 newtons all the way up, 1 meter. So I've displaced it 1 meter, so that's 10 newtons times 1 meter. And that's what work is. Work is lifting something. Work is force times a distance. Okay? So force times displacement. And displacement here, that's a change of the position. In my example there, I changed it by 1 meter. So I can use the letters W is equal F times D. W is equal F times D. And right underneath here, since I already have the words work equals force times displacement, W is F times D, I'm going to put square brackets here. This is a habit we're going to get into now. And the square bracket means I'm going to pull out the units. And the unit of work, you know what, let's stack this on top of each other so that it's one on top of the other, okay? Because this is just a column of equivalences. Okay. So we have here the unit of work, here I'll keep going, is the unit, and the unit of force is the Newton, and the unit of length or displacement is the meter. So the Newton times the meter is the letter J, is the joule. That's the name of a French physicist, okay, joule. Okay, so how much work did I do when I lifted this thing 1 meter? 10 newtons times 1 meter. I did 10 joules of work. Lifting something 10 joules of work. Okay. So, example. And by the way, this is what all energy is going to reduce to. So this lifting thing is not too humble of an example. So lift 10 newtons, 1 meter. And what I'll do is I'll even draw my 10 Newton weight here, and I lift it. You know, I can even say I lift it and put it up on a shelf. Here's the shelf. 10 newtons, there's the hook on it, right? And I brought it up there. So that is the definition of work. It's not quite complete, but it's a start. So when you climb the stairs, you're doing work. When you walk up a hill, you're doing work. When you just lift something, of course, you're doing work. You do pull-ups and push-ups, you're doing work. So that brings us to the next detail on this. So for that, I'm going to bring out a more impressive weight. So we have the physics department bowling ball. Okay, so I bring out the bowling ball. And let's see here. I'm going to drop it on your foot. It weighs more than 50 newtons, by the way. This scale is up to 50 newtons. And going all the way around. Whoa, I don't want to damage it. So what I did was I brought two 50 Newton scales to see if we can split the weight between these two scales. I haven't done this before, but what could possibly go wrong? Okay. Can I hold these both at the same time? See, I'm seeing 40 on one. See, if I see 30 on that one, I see 35 on that. So it's 65 or 70 newtons, okay? Okay. Actually, was I standing in front of the camera? That's the question. Okay, there's the thing. So I can add these up in different ways, but it's somewhere around 70 newtons. Okay, so here's a question this table top is 2, just over 2 newtons, 2.3 newtons. And I have 70 Newton bowling ball. And what I'm going to do is lift it from here, just over the table, and bring it across and put it down again. Okay. So I carried it the length of the table. Did I do 2.2 times 70 newtons of work? The answer is no. This was a trick question, because I could have just rolled it across here without any effort whatsoever. Okay. So lifting it a centimeter above the table and going across, somehow that doesn't seem like a very reasonable thing to do. I could have just rolled it with no effort. So the addition to our definition is that the work and the force and the displacement have to be in the same direction. Okay. So if I lift this bowling ball by 1 meter, okay, then I'm going to do 70 Newton meters, 70 joules. Okay. But if I go horizontally, I'm not going to be doing any work. Okay, so that detail, let me write that down for you. And we'll see, it plays a role. It's not just a subtlety. 1 meter, so note, in we'll say in physics work, I'll call it physics work instead of physical work. Okay, in physics work, the force and displacement must be parallel. The force and displacement must be parallel. That's not B, that's B. Parallel. Okay. Force and displacement must be parallel, so we can say F is parallel to D. We can think of force and displacement as vectors, and force and displacement are parallel. So the nice example for this is a stairway. So suppose I have, and I'll have just enough room here, so I'll start here. Suppose I have a stair and a stair steps, and I want to bring my bowling ball up to here. So I start here, there's my bowling ball, and I roll it, and I bring it here, and I did some work. So I lift it here, then I roll it to here, no work. I lift it, did some work, roll it, no work, and all the way the same, and finally I end up here, and how much work did I do? All of the horizontals involved no work, but the total vertical distance h was work. So if I take the ball up the stairs, so I carry the ball up the stairs, say, in the way I just described, then the work, I'll write it in here where I have space, is equal to the weight of the ball, which I'm just going to say F, the weight of the ball is F, times the height that I went. And the same thing goes for an incline now. You can say an incline is kind of a limit of these stairs. So the next example that goes along with this one is if I roll the ball up the stairs. And I'll put a shelf up here so I can keep it there. If I roll the ball up the stairs, and I end up right here, then again, the forward direction didn't matter, it was the vertical. I could have rolled it effortlessly at the bottom and lifted it up all at once, or I could push it up the stairs right there. So again, work is equal to FH and suppose we wanted to push a car up a hill. Well, you better hope the hill isn't that steep, okay? You definitely can't lift the car up the hill. You can push it up the hill, but it's going to be the same amount of work. You may just have a longer incline, and that tells us that we're going to have a mechanical advantage on the incline, essentially the same as we had with the lever. Essentially the same as the lever. Let's make that clear, and then we'll have a good understanding of work. You just lift things, you've done work. Okay. So, the same work by two different paths. So the same work by two different paths. This is going to put these examples together. So now we're going to have a triangle here, up and down, vertical thing. And we're going to take, we'll call this A, B, and C. So we can take the ball up the slope here, and we can say W, A to C is equal to F1 times the displacement, which is going to be the hypotenuse L. So the force to roll it times the hypotenuse L, the work A to B to C is that we roll it along here and then we lift it. And this is H. That is equal to F2 times H. Okay. But the same work by two different paths means that F1L is equal to F2 times H. Okay. Now we could get into trigonometry here, but we actually don't have to. We have a well-defined triangle. Okay, we know the Pythagorean theorem, we know similar triangles. So it's just the point that F1 is small and L is large, or F2 is large and H is small. Okay, there's an equal sign here. Both of these, for example, if it were the bowling ball, and H is 1 meter, then remember 70 times 1, so both of these would equal 70. So this is mechanical advantage. I'm going to leave it there. It's better that we just leave that expression rather than start solving for other things. So note the incline gives mechanical advantage, just like the lever does. So there's different ways to do the same work. You know, if this were a car, you'd want to push it up a long incline. You certainly wouldn't want to lift it. Okay. So yeah, this is a really important topic here, that we can get the same work by different paths. And also, you know, we're doing a lot of simple formulas, and you want to get used to it. Hopefully you're already getting used to it because we've done so much of this. Big pictures, nicely labeled. Put in some more definitions if you have time. And but this is the level of math we're doing the whole semester. Simple, you know, product equalities, divide by, stuff like that. Okay. Not going to go too much longer today either. But yeah, now that we've set up work, I can finally bring these other definitions in. So we now know what work is. We have some examples. I think they make good sense. Lifting something, including yourself. I weigh 900 newtons. You know what? I'm now going to, that's an example. Here, that came to mind. So I'll make that the final example here of the work, and then I'll bring a couple more definitions. Okay, so one more example. This one will come into play a lot. So now I'm going to talk about a stair climb, and I'm the one climbing the stairs. So let's just say I'm 900 newtons. That's my weight. Okay. Force, 900 newtons. That's my weight. And the stair, H is 5 meters. You know what? Because I have a certain number in mind, I'm going to say I weigh 800 newtons. Truth is probably somewhere in between. 800 is a better number for us, okay? 800 newtons, that's my weight, and I climb the stairs. How much work have I done? Work is equal to 5 times 800, so 800 newtons, 5 meters, 4,000 Newton meters, which is 4,000 joules. So the stair climb, you lift yourself, that's how much work was done. Okay, so now I'm ready for the big punchline. Actually, when we get to the theory of heat, which we're going to need later on, thermal physics, this 4,000 joules is very close to what we call a food calorie. Okay? But right now, this is just mechanical work. And so the theory of heat has not even yet been touched on, but that's one of the reasons I use this 4,000. It's a good number in that regard. So let's remind ourselves that this is mechanical work. And now I'm going to define energy. Energy is defined as the capacity to do work. Do work. So the energy is not actually a thing. Okay. But if I have enough capacity in me to climb these stairs, then I have at least 4,000 joules of energy in me. And when I've completed the stair climb, I've done that much work. So energy is the capacity to do work. What we're going to see is that there's all manner of ways to do work. It's also possible to store work. So that's our definition of energy. We're going to add to that definition later on in thermal physics, but for now, this is the fundamental definition of energy. It's the capacity to do work. The units of energy, I'll just write the square bracket there. The unit of energy for this class is the joule. Okay. And finally, I'm going to say, I'm going to ask, can work be stored? Because then stored work is a form of energy called potential energy. So I'll finish with this thing here. Stored work is called potential energy. Potential energy. There's our expression. So now we're finally at the whole energy thing, and you can imagine that we need energy to do anything. To build a building, if we build something, we're lifting mass up off the ground to a higher height. That's work. You know, if we want to get ourselves to the 10th floor in a tall building, take the elevator, that's work. We want to drive up a hill, that's work. So you can see the necessity of energy to run, to run life, to run our civilization. And we're at a stage now in history where the amounts of energy used are utterly enormous, but you can see we're starting from these utter basics. We're going to move through all the way up into the modern world. Okay, so this is where we are right now. We know what mechanical work is. We have some good examples. We now know that energy is the capacity to do work. That is our definition. And we're going to bring in more and more examples. Okay, good. I'm going to call it a day, and we'll see you next time.